Hello everyone, welcome back to the tutorials on Ansys Workbench. Moving on to part B. So here we are finding the natural frequency, mode shapes, and also we will do some harmonic analysis on the beams. Maybe a simply supported beams, or it may be a cantilever beam of different cross sections. So before getting into the problems, first we will know what you mean by the natural frequency and what is mode shapes and modal analysis first. So as I said, I am not going to cover in depth about these concepts. I am just going to brush you about the concepts of this natural frequency, mode shapes and modal analysis. So coming to the natural frequency. So before explaining this natural frequency, so consider an example of a spring mass system. So in the first image you can see the spring, one end of the spring is constrained and the other end of the spring is free. K is referred as stiffness of this spring. So when mass has been attached to the free end of a spring, due to the self weight of this mass, the spring will get stretched. So this deflection we refer it as delta. So it is referred as static deflection. Next, after giving some initial displacement x to this mass m, so now the displacement of this mass is x. So after giving this initial displacement without applying any external load, this body will start oscillating. Oscillating in the sense, this is the mean position of this mass, this line. So it is going to oscillate along with this axis to and fro. So this oscillation is referred as vibration. So after giving that initial displacement, the body will start oscillating. So that is referred as natural vibration. So corresponding to that natural vibration, we have natural frequency. So the frequency of a natural vibration is referred as natural frequency. So remember, after giving some initial displacement, the body will set to under natural oscillations. That is referred as natural vibration. And if you are applying the external force periodically, then it is referred as forced vibration. It will not come under free vibration. So that is what a natural frequency is. So the definition is, the natural frequency of a system is the frequency at which it tends to oscillate when disturbed and then allowed to vibrate freely without external forces or damping. So it is an inherent property of the structure determined by mass and its stiffness. So what is the importance of finding this natural frequency? So these are some of the importance of finding the natural frequency of any structure or any machine component. The first one is resonance. So in order to avoid the resonance, we should find the natural frequency of a structure or a machine component. So resonance again. So what do you mean by this resonance? Suppose if a system or a structure is subjected to some periodic external forces or any external excitation, if that external excitation is matching to its natural frequency of a structure or any machine component, definitely the amplitude will reach to the infinity, which means the machine component or a structure subjected to resonance. So at the time of resonance, you can expect the large amplitude oscillations and definitely a potential structural failure will happen. So that is what a resonance means. So that is why it is very important to find the resonance and the natural frequency. Both should be far away from the values. Second importance is structural health monitoring. Suppose if there is any changes in the natural frequency, definitely it will indicate the damage of a structure or any machine component. So that changes, it may be in the form of stiffness or any mass alterations happening in the systems. So that is why natural frequency is important to find in health monitoring of a structures or any machine component. The third importance is design optimization. Like Ansys always ensures that the natural frequency is far from the operating frequency of the machine components or any external forces. As I explained in the resonance, these two values should be far away in order to ensure the proper operations of a machine component or any structure. So that helps in design optimization of a structure or it may be any machine component. So that is why finding the natural frequency is most important. So these are some of the importance of finding the natural frequency. So next comes the mode shapes. So the mode shape describes the deformation pattern of a structure when it vibrates at a particular natural frequency. So remember this word, at a particular natural frequency. So in the below figure you can see the mode shapes of a cantilever beam. So this is a first, second and a third mode shape. So each mode shape corresponds to the natural frequency of a cantilever beam. Like first mode will correspond to one natural frequency, second mode second natural frequency, and the third mode refers to the third natural frequency. So each natural frequency has a corresponding mode shapes. So this is what a mode shapes is. So this is the deformation pattern of a structure. So what is the importance of finding these mode shapes? So first one is understanding the vibration patterns. So like in this figure you can see, visualize, so how these different parts of this structure or a cantilever beams move relative to each other. So like this is the reference beam. So how these parts are moving with each other. So it is visualize how different parts can be moved in a structure. So the first importance is understanding the vibration patterns. The second is effective design. Like if you are finding any harmful deformations in this specific modes, in any of the modes, so then you can able to redesign or you can able to modify the designs. So that is one importance of finding the mode shapes. And the third importance is structural analysis. Like if you are finding the mode shapes like this, it will be useful and it will be helpful for placing some kind of supports and some kind of dampers, or if you are applying any dynamic loads on these structures. So by help of these mode shapes you can able to analyze this structure completely. So it will be helpful for understanding mode shapes, for placing the supports of dampers, or for designing some kind of dynamic loads. So that is what the importance of mode shapes are. So next comes the modal analysis. Like modal analysis is a technique used in engineering to determine the dynamic characteristics of a structure or any mechanical system. So it involves analyzing the natural frequency, mode shapes and damping of a systems, so which are critical for understanding how it responds to the vibrations. So like finding the different mode shapes of a structure or any machine components and analyzing those mode shapes for any failures, that refers to the modal analysis. So these are some of the key concepts of modal analysis. First one is natural frequency. So we have discussed about this natural frequency, and the second one is mode shapes. We have already discussed about this mode shapes, and finally comes damping. So damping is actually a process, or it is the resistance offered to the motion of a body or any machine component. So that is referred as damping. So the material used for damping is referred as dampers. So it may be a springs, it may be a shock absorbers, or it may be a rubber. So these materials are referred as dampers. So damping is a process. So while damping, there will be a energy dissipation happening in the system, so which obviously reduces the amplitude of vibrations over the period of time. So this damping actually helps in controlling the vibration and also prevents the resonance occurring in the structure or any machine component. So this is the key concept of this modal analysis. So we will solve one problem on finding these natural frequencies and mode shapes. So the first problem is fixed beam for natural frequency determination. So obtain the first 10 natural frequency of the fixed beam shown in the figure and also plot their mode shapes. So this is the cantilever beam. So the length of the cantilever beam, so it is not cantilever beam, fixed beam. So length of this beam is 1 meter and the cross section is square cross section 0.01 meter, 0.01 meter. So modulus of elasticity E 200 GPa, Poisson ratio 0.3 and density is 7830 kg per meter square. So let's solve this problem by using Ansys Workbench. So open the Ansys Workbench, and in the analysis systems just check for the modal analysis. Here we have modal analysis, so click and drag it on the screen. So rename this modal analysis 1. So next double click on engineering data. So density is 7830, Young's modulus 200 GPa, Poisson ratio 0.3. So this is 7830. Yes. So this is 200 GPa and Poisson ratio is 0.3. So you can close this engineering data. Next, right click on geometry, new design modular geometry. Select XY plane, look at face, go for sketching, line. So this length of a beam is 1 meter. So dimension, select this. So this is 1 meter. Click on generate. So now the cross section of this beam is a square cross section 0.01 meter. So go for concept, cross section, rectangle 0.01 meter. So just click on generate. So you can observe here cross section has been created, but we have 0 parts and 0 bodies. Means, so whatever the line we have drawn is not considered as a body, because whatever the drawing we are drawing on this working plane, those are all considered as sketches. And always remember, these sketches has to be converted either to the lines or to the surfaces. So now I want to convert this sketch into lines. So to do that, go for concept, lines from sketches, select the line and click apply. So observe here. So I will click generate. So now we have a part, we have a body. So just expand this and click on line body. Now I want to assign the cross section for this line body. So rectangle 1, then click on generate. So now geometry is completed. Minimize this, go for workbench, double click on model. So geometry is imported successfully. So you can click on this cross section to see the complete 3D view of a beam. So directly I will go for mesh, right click, generate mesh. So meshing is done. So next I want to fix both ends of the beam. So go for model, insert, fix support. So you can zoom this and select the vertex. So select this vertex, rotate it, press Ctrl and select this vertex, click apply. So 2 vertices are fixed here. Next click on analysis settings. So in the problem, 10 natural frequencies and their mode shapes. So corresponding 10 mode shapes we will get for 10 natural frequencies. So now click on analysis settings, maximum modes to find is 10 here, and limit search to range is not defined, so let it be no. And damped, so there is no damper found in the problem, means it is completely under undamped vibration. So damped, no, we have not used any damped here. So next go for solution. So right click and directly go for solve. So in the table you can see the 10 modes and the corresponding natural frequencies for their mode shapes. So now I will just select this data, all 10 natural frequencies, right click and click create mode shape results. So now you can observe the total deformations of the individual mode shapes. So now again right click, evaluate all results. So now you will get the deformation for that natural frequency. So the first frequency is 51.916 and its displacement, maximum displacement, is 56.47 mm. Next, the second mode shape, and this is the deformation for the second mode shape. And you can observe the values. The first natural frequency and second natural frequency are same, but the deformation is different. Okay, sometimes these values are very close and sometimes they are equal, so it is almost same like this. So we have 10 mode shapes, so you can just click on all the mode shapes, and if you want to play the animation, you can play the animation. Now so we have 10 results here. So in order to take a printout of these results, so just change this viewport, change the viewport to 4 viewpoints or viewports. So now click on first one and click total deformation 1. Next second one, total deformation 2. Next third one, total deformation 3. And the fourth one, total deformation 4. So now view I will make it front view. Front view, change this to front view, front. Okay, by default it is coming like this, so change the viewport to one viewport, right click, view, front. So now I will change the viewports to 4 viewports. Okay, so you can check this is 1 and check for 2 and click for 3, and this is for 4. So now to save the results, go for results, images. Here don't save this as image from file, because we have 4 files in the same screen. So you should use composite image to file. If you use this, you will get only one result at a time. So I will use this composite image to file, click. Okay, so I don't want to see the interior borders, so you click here and click OK. So in the desktop I will save this as ABCD, save. So next results, viewports, so you click here, change this for 5, change this for 6, click here 7 and click here 8. So now again go for results, image, composite image, interior borders are not required, click A, B, C, D, E, F, save. Next remaining 2, so display, viewports, so 2 horizontal viewports, sorry vertical, if you want vertical you can use vertical. So click this, so this is the 9th one, sorry 8th one and 9th one. Okay, we got only 9 here. Okay, so 10th one is, I think I forgot to have this. So while selecting, please select the entire mode shapes here. So this will be the 10th one. Okay, so later you can go for result, images, composite image to file, interior borders. Okay, FGH, save. So this is how to save the results. So now you can go back to the screen. Here you can see this. So all 4 results in a single sheet. So this is first one and second one. If you want to play the animation, you can play the animations. So that's all. Thank you. See you in the next video.